All right, let's jump right in. Your physics exam is literally just around the corner, and what we're going to do right now is a last-minute, high-impact polish on those first two chapters. This isn't about relearning everything from scratch. Nope. This is about sharpening what you already know into actual points on the page.
So why this number, 18? Because that's about how many marks are up for grabs from just these two chapters alone. Think about that. That is a huge chunk of your paper, and we are going to make sure you lock in every single one of those marks.
So here's our mission for the next couple of minutes. We're going to clarify the core concepts you absolutely have to know. We'll shine a big spotlight on the common pitfalls, the places where students lose easy marks when they're under pressure. And I'm going to arm you with some simple memory hacks to pull those crucial formulas out of your brain when it really counts.
Okay, first up, Chapter 1, Electric Charges and Fields. I want you to think of this as our offensive playbook. These are the core plays you've got to have down cold.
These right here are your three non-negotiables. You've got Coulomb's law, which gives you the force between charges. Then there's superposition for when you have multiple charges. And remember, you've got to add the fields as vectors, not just plain numbers. And finally, Gauss's law. This is your elegant shortcut for any problem that has a nice, high degree of symmetry.
Okay, let's talk about where points just vanish. First, simple sign confusion. Come on, you know this. Electric field lines always point away from positive charges and towards negative ones. Get that right every single time. Second, don't try to force Gauss's law where it doesn't belong. If it's not an infinite plane, an infinite cylinder, or a sphere, it's probably the wrong tool for the job. And lastly, that dipole approximation, you can only use that 1/r³ formula if the distance r is way, way bigger than the dipole separation d.
So, how do we burn these formulas into our memory? Easy. For a dipole's axial field, just say it out loud with me. 2p over r. That's your 2p over r³. For an infinite line, just picture a tube of lambda lines. To remember that lambda, the charge density, goes on top. And for an infinite plane sheet, sheet equals SPA. That'll help you remember sigma over 2 epsilon naught.
Now let's really test that understanding. Quick question. Why does the dipole field drop off as 1/r³? Well, it's because from far away, the positive and negative fields almost perfectly cancel each other out. And look at the logic from question 16. This is so important. With Gauss's law, the total flux depends only on the charge you've enclosed, not the shape of the surface around it. All right, playbook part 2. Let's shift gears to electrostatic potential and capacitance, and you'll see how this builds directly on what we've just covered.
So here are the new key players on the field. First up, potential, or V. And you know what the best part is? It's a scalar. That means no more messing around with vector directions. It's just energy per unit charge. Next, the workhorse of this chapter, the parallel plate capacitor. Its capacitance is all about its shape and size. And finally, the energy it stores. You got to know all three ways to write this equation. More traps to watch out for. First, the sign of V. It's so simple. If the source charge is negative, the potential is negative. That's it. Second, dielectrics. This is a classic. When you stick a dielectric in, the electric field inside gets weaker by a factor of kappa. That, in turn, allows the capacitance to get bigger by that same factor. And seriously, please don't mix up your units. Farads and volts are not the same thing. Time for a few more memory hooks. Want to relate potential and field? Just remember that V is the integral of E. So you can think of it like this. V is the area under the E versus R graph. For the capacitor formula, just picture an A over D sandwich, the area A over the distance D. And for energy, the one you're probably going to use most often is simply half CV squared. Let's lock this in with the quiz highlights. Check out these relationships. Question 6. If you cut the distance between capacitor plates in half, what happens? The capacitance doubles. It's an inverse thing. And question 11 is so critical for any calculation. Energy is proportional to V squared. So if you double the voltage, the stored energy goes up by a factor of 4. Getting a feel for these dependencies is going to save you so much time. Okay, we've gone through the physics. Now let's talk about exam technique. This is all about how you take what's in your head and turn it into the most marks possible. It's about playing and winning the marking game. This right here is probably the most crucial distinction to make. You absolutely cannot mix up field and potential. Look at the slide. The electric field, E, is a vector. It tells you about force. Potential, V, is a scalar. It tells you about energy. Getting this difference right is fundamental. It's everything. Let's get a real feel for this. Don't just see capacitance as some formula. Think of it like a bucket. A capacitor's capacitance is basically its charge-holding capacity. A bigger capacitance just means you can store more charge for the same amount of electrical pressure, which is just the voltage.
Here is exactly how you make the examiner's job super easy, which means more marks for you. Number 1, always start by stating the fundamental law you're about to use. Number 2, a clean, well-labeled diagram is non-negotiable. Seriously, it shows you get the setup and can be worth a mark all by itself. And number 3, when you get your final answer, put a big box around it. Make it pop right off the page so they can't miss it.
All right, final sprint. Let's do a rapid-fire drill of our key mnemonics. We're going to burn these into your brain for exam day. You ready? First up.
For the dipole's axial field, our trick is 2p over r.
For the infinite line charge, you're going to picture the tube of lambda lines.
The parallel plate capacitor formula, that's our easy A over D sandwich. And for the energy it stores, your go-to is half CV squared.
And just remember the system for every great answer. You state the law, you show your setup, probably with a diagram, you walk them through the derivation, you box your final answer, and if you have a second, add a single sentence of insight. That, my friends, is a perfect score answer. So, there you have it. The key concepts, the common mistakes to dodge, the memory hacks, and the strategy to absolutely maximize your score. The playbook is now complete. The only question left is, how are you going to execute the plays?
You have put in the work. Trust your preparation. I want you to walk into that exam room with confidence. You've got this. Good luck. Go ace it.